welcome to Unit 6. And in Unit 6, we're going to be doing topics that relate, of course, to everything else we've done in AP Calculus. And I know that you're very familiar with this word called slope, or aka our lovely D word in calculus, the derivative. And in this lesson, I want to talk about something called a slope field, and this guy's name, you might think is Euler, but it's actually pronounced Euler. If you are an Edmonton Oilers hockey fan, that's how I remember how to say his name. But Euler's method to figure out changes in y. We'll talk about that on page 3, but today let's start off with this thing called a slope field. So what is a slope field? Well, really it's just a graphical representation. So you're going to be drawing graphs of a set of slopes obtained from a differential equation. So remember, the differential equation is just that dy dx thing, and that's what we're going to be trying to graph out. Not the original graph, not y equals to, but dy dx, and that's the idea. So if you cannot separate the variables and integrate, we can still use a differential equation to plot slopes of a function. So in example number 1, look what I've told you here. I've got this equation, dy dx, the differential equation, is equal to negative x over y. And I want you to find the following slopes at the given points. So we did this way back when we did like implicit differentiation. What you need to do is just plug in the points. So we plug in 3, 2. Let's see what you get. You get negative 3, 2. For the b value, it's negative of negative 1, so that's 1 over 3. Negative and negative 2 is positive 2 over negative 1. And 2, negative 2, if I plug it into the equation here, that's just 2 over negative 2. Sorry, negative 2 over negative 2. And interestingly enough, that is just equal to 1. So if I asked you now to actually plot these points, and I think that's what example number 2 is about, at the specific values, you've got 3, 2. So look, at 3, 2, that's this point right here. What should the slope be? It's like negative 3/2. So how do I show a negative 3/2 slope? Well, remember, if m equals 0, you've got a flat line. If m equals to 1, you've got kind of like a 45-degree line. If m equals to negative 1, it's a negative sloping 45-degree line. This is negative 3 over 2, so it's steeper than a 45-degree line that's negative. So I think probably something like that. Okay, and that's from this point here. Okay. At negative 1 and 3, that's this point. Notice the slope here is kind of flat, 1/3. Right? And then you see at negative 2, negative 1, that's this point right here. The slope is very steep, so that's negative 2. And then at d, 2, 2, so that's over here. Notice that I need to now draw on the slope of 1. Okay? Oops, I forgot to answer this question. Why can't you find slopes when I equals 0? Think back to good old times in grade 10 and 11 math. Yes, you can't divide by 0. So, in example number 2, I'm asking you to plot the slopes for all these marked points on the coordinate plane. So you see how these dots are here and they don't have those little dashes? Those dashes are the representations of the slopes. For the ones that are missing, that's like here, 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 here. I'd like you to actually now go ahead and plot the slope fields, or these little dashes. Okay? And once again, all you need to do is just take that coordinate and plug it into our differential equation. Okay? So you go ahead and do that, and then when you're done, come back and check your work with me. You should have something like this. And once again, at 0, nothing, no slope field at y equals 0. Once again, that's y. Dum 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 dum. Notice at this point when x is 0, all of these are flat, right? here x equals 0, so that's why the slope dy dx is just 0 over y. Who cares what y is? It's still 0. And then let me just try to finish off the rest of these for you. A little bit steeper, steeper, steeper. Cool. There you go. Did you get that? Good. If you didn't, make the changes. You probably just plugged the numbers wrong. Now, for example 3, it says in example 2, you made what is known as a slope field. So that whole visual picture is what we call the slope field. It says starting at the point 0, 1, I want you to follow the flow of the slopes. Okay, think of it like the river, water flowing. Follow the flow of the slopes to sketch the solution curve containing 0, 1. So now I'm saying, look, I want you to find a specific curve that involves the point 0, 1. Well, where is 0, 1? That seems to be right here, this point. So I want you to kind of follow the flow of these and try to sketch the curve. It says your graph should be parallel to the slope lines and be like an average of the slopes whenever it goes between the lines. It says your solution curve must represent a function whose domain is the largest possible open interval. So remember, the idea of a function is for each x value, there's only one y value. But of course, it must contain the given point. So sketch the solution curve also passing through these other 2 points, negative 1, 1, and 1 passing through 0, negative 3. Okay? So as I do the first one in green, watch. Here's 0, 1, and it looks like if I move to the left, the slope fields are going downward. So I guess my curve kind of goes down, down, down like that too. And if I move to the right, you see this one here? I have to be parallel to it. So I have to kind of be parallel, so it looks like it's going down, 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 down. And I think that's all I can do, because remember, at y equals 0, there is no value, so I'm going to put an open dot. So I think my curve looks kind of like this. Okay? I could do the same thing now with negative 1, 1. So where's negative 1, 1? That's this one right here. So as I now can look at this, if I go towards here, see it flattens out. So it has to be parallel here, flat. And I guess it probably comes like this. And once again, I don't want to continue further down here. I could, but it's supposed to be a function. And remember, the goal is to draw the one with the function with the largest possible open interval. So probably something like that would be cool. And then the last one I'll do in red, 0, negative 3. So here's 0, negative 3. I'm thinking, okay, let me draw some crazy solution curve here. It looks like I'm doing something like this, maybe ending up here. And there's the curve of the function involving the point 0, negative 3. All right. Now, let's see if we can now solve the differential equation. So that was the visual representation of it. Okay, so let's actually solve it. Well, how do we solve stuff like this? Hopefully, remember last unit where we wanted to separate our variables. So I'll keep dy on the left side. I'll actually move the y to the left side, so that's y times dy. And then I'll move the dx to the right side, so that's negative x dx. Once we separate the variables, the idea once again is to integrate both sides. So you integrate and you integrate. And we integrating y, we get y squared over 2. And then integrating negative x, that's negative x squared over 2. Don't forget we have this plus c. And if you really want to solve for y squared but not y, I guess y squared equals to double of that. So 2 times the negative x squared over 2 is just negative x squared. And notice if I have a c and I times it by 2, it's still a constant. We could say it's 2c, but 2 times a constant is still a constant. So let me just call it some other constant. I don't know, I'll call it like c1 or something like that. Okay, just to know that it's still a constant, but it's a different constant than plus c. All right, so solving for y. If I ask you to solve for y now, that's what I said here, I have y squared. I guess y equals to the square root of negative x squared plus c1. And I actually forgot one thing. You should have a plus or minus. So noticing here, I've got y equals to the positive value of negative x squared plus c1, or negative of the square root of negative x squared plus c1. Okay? And those are the particular solutions. This is the actual solution for all different possible curves. And notice on my picture here, I've drawn 3 particular curves, the green one, the blue one, the red one, because of the idea of these 3 points. Okay. All right, so let's find the particular solution for this differential equation that passes through 0, 1. That was the one in green. So if I asked you to find that, all you need to do is solve for c by plugging in the point 1 for y and 0 for x. And notice you just get 1 equals to c1. So therefore, I'll say the equation is y equals to the square root of negative x squared plus 1. Some people like to write it as 1 minus x squared. I'm okay with that. And notice this equation then represents the green graph there, which I think makes sense. It's half a circle with radius 1. Okay. Trying the next one with the 0, negative 3, same business, but this time because it's 0, negative 3, I should use this second equation, the one that says y equals to negative root negative x squared plus c1. So negative 3 equals to negative of 0 plus c1. Then negatives cancel out. I get here the square root of c1 is 3, or c1 equals to 9. Therefore, the particular solution for this one, where the graph goes through the point 0, negative 3, is negative root negative x squared plus 9. And I hope that makes sense to you, because that really is the half circle that is below the x-axis. Yeah. All right, let's keep going. Next page. So, in example 5, I'd like you to now try this yourself. For the differential equation y prime equals to 1 over y, I'd like you to draw the slope field in the dot coordinate plane to the right. Then I'd like you to graph particular solutions, and then I'd like you to solve the differential equations, and then I want you to write the functions as particular solutions. So pretty much the same as example number 4, and I'd like you to try this yourself. The only difference here in this one is that there is no x value involved. So really, all we have to worry about is the y value. Okay? So go ahead and please try this yourself, and then come back and check your answer with me. So notice here, everybody, this y value is 3, so the slope for all of these points in this area here would be 1 over 3, so 1/3. Okay? This is y equals to 2, so m equals to 1/2 for all the points in that row. M equals to 1. Once again here, no slopes. I hope you can see the idea here. This actual slope field is much easier to draw than the one I gave you on the previous page. Say thank you. So 1/3. Let's do 1 first. 45 degrees, 45 degrees, 45 degrees, 45 degrees, 45 degrees, 45 to 45. Half would be a little bit flatter. Flatter, 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 flatter. 1/3 is even more flat, 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 even more flat. And I hope you can do the ones underneath. Sweet! You graph the particular solution going through -2, -1. -2, -1 is this point right here. I guess I'll follow these curves. And it looks like this. And I guess it comes to the y-axis and has a hole. I'll use blue for 2, 2. 2, 2 is here. I guess I should follow the curves like this. Sweet. Maybe it goes somewhere here like that. Okay. Guess I should have arrows on the end here, so they do probably keep going, going, going. Solving the differential equation, once again, this is dy dx equals 1 over y. Separate your variables. Integrate. Y squared over 2 equals, the integration of 1 is just x, so x plus c. Once again, y squared equals to 2x plus a new c1. And if you do the square root, I guess it's just 2x plus c1. Don't forget plus or minus, depending on what you choose. So once again, the one in black, I'd probably choose the square root with the negative in front of it, y equals to negative root 2x plus c1. We'll plug in the point. Negative 1 equals root 2 times 2, negative 4 plus c1. So that's 1 equals to the square root of negative 4 plus c1. We square both sides. I guess I don't have to show you all these steps, but I'm going to anyways. You get the c value being equal to 5. And then for y equals to negative root 2x plus 5 is the equation in black. And the one in blue will do the same business. This time I'm using the positive root. Look at this. The constant is 0. And that makes me happy because I did draw my blue graph where it does go through, or pretty much touch, not go through, but touch 0, 0. Yay! See how the picture matches the algebra? Isn't life great? Say yes. Okay. 2 other types of questions you'll get. I could actually give you the slope field, and it's your job to figure out which differential equation, so once again, the differential equation, the slope, matches up that picture. Okay? And by going backwards, what you could do is just look at the ideas of slope fields. And my hint to you for this one is, I see this here on the x-axis. This looks like the slopes are all equal to a value of positive 1. See that 45-degree line going positive? So slopes are 1 on the x-axis. And that's, of course, when y equals 0. So that's one key interesting thing I see. And then I'm going to ask you which one of these, A, B, C, D, E, also have a slope of 1 when I plug in y equals to 0. Okay? So I'm not going to actually give you the answer here. I know, you just want the answers. But I want you to think about this one and then choose an answer. And we'll come back to class and I'll see if you're right or not. Okay? Maybe there'll be prizes involved. Who knows? Okay, so try it, please. And then after you're done, come back and I'll give you a hint for also number 7. Okay, number 7 time. So this question is similar to 6, but one small difference is there. Notice it says the slope field of a certain differential is shown. So once again, these are slopes, just like example 6. But now my answers are not the differential equations, but the actual specific solution. So what I'm saying to you is this. I want you to find me the actual function y, not dy dx. This is a graph, so these lines represent slopes or dy dx. And then from there, can you figure out the actual specific solution? So that's like me up here in example 5, drawing this specific solution in black and blue. So my suggestion to you here is see if you can just trace along one of these points and create a graph. And then when you see that graph, tell me which equation here, A, B, C, D, or E, best represents this graph. And this is why we need to learn all that graphing in Math 12. Okay, so once again, I'll leave you with this. Try it, then come back, and we'll talk about this guy named Euler. All right, you're still with me, I guess. That's great. So one more page and we're done for today. Let's take a look at this idea called Euler's method. So this is a method that allows us to graph an approximate solution to a differential equation. Once again, you know, we did exact solutions on the previous page, but we can't do that all the time. And so a lot of times in calculus we try to approximate things, and here's the way of doing it. So let me show you example number 8 and 9, and then perhaps you can try 10 and 11. So it says here, use Euler's method to construct an approximate solution for the differential equation. So this is our differential equation, dy over dx is equal to y. And I want this particular solution starting at a particular point, 0, 1. And to do this, instead of just randomly drawing slope dashes, I'm going to actually use a chart and try to methodically go from 0, 1 and move to the right to continue to draw what this graph looks like. So I like you, whenever you see this kind of stuff, to set up a little chart. Here's our x and y values, and we're starting with the x value of 0 and 1. Okay? And then I'm saying to you, hey, can you actually calculate the derivative at that particular point? Well, to calculate the derivative at that point, you just plug it into the formula. In this case, it's just y, so I guess it's just 1. And then what I'm going to ask you to do now is, hey, we're going to increment x. We're going to change the value of x by a step size of 0.1. Okay? And my question to you is, when I change x by 0.1, how does the y value change at that particular point? And the change in the y value is always just the slope times delta x. So the slope is the number in the previous column, 1, and then delta x, of course, is 0.1. So this delta y is just 0.1. So what I'm saying here is this. You started with the point 0, 1. That's right here. When I move a step size of 0.1, so when I move 0.1 to the right, the y value has also changed by 0.1, so 0.1. So here's my new point. Okay? Now I'd like you to take that new point. So the new point now is 0.1, because I changed the step size of x by 0.1. And the y value change was also 0.1, so 1 plus 0.1 is 1.1. And now we're going to repeat the process. Okay? So the dy dx is just y. In this case, it's 1.1. The change in y is now 1.1 times the delta x, and that gives you 0.11. And so now for my new point, the coordinate is going to be 0.2 for x, but my y value is 1.1 plus 0.11, which is 1.21. So notice now if I go another step size of delta 1, it's gone up 1.21, so just a little bit more than 1. It's at now 1.21 right about there. Okay? And I'll do it one more time. So this is 1.21. 1.21 times the delta x. That gives you 0.121. And so if I asked you to go 0.3, I believe the y value is 1.331. So going one more to the right. Now we're at 1.331. So these are your 4 points. And then I guess I would just try to connect the dots. And this would be my solution to the equation. Okay, probably not concaving down, but like this, concaving up. Okay, so ultimately if I asked you, hey, what is the y value when x is 0.3, you could now say, hey, by looking at this final part, the y value is actually approximately 1.331. Okay. Now, these are my approximate values. If I asked you for the actual values, you would have to take that differential equation. So let's look at example number 9, and solve it algebraically. So once again, separate the variables. This is dy over y this time, equals to dx. Integrating both sides. What's the integral of 1 over y? Did you say ln y? Yeah, I hope you did. Make sure you put the y in absolute values, because you can't take the ln of a negative number. This now just becomes x plus c. Got to get rid of that ln, so now we'll take e on both sides. Remember all this stuff here, friends? And e ln is just y, so the absolute value of y equals to, in this case, e to the x plus c, or e to the x times e to the c, and that's just another constant. So we can call that whatever you wish. Y equals to c1 e to the x. And because I have a particular solution at 0, 1, I can now plug in 0, 1 to solve for c1, and I think you get y equals e to the x. Okay? All right. And then if I asked you for the actual values, you'd be plugging in now. This will be e to the 0.1, which is, I think, 1.105. This is e to the 0.2, which would be 1.221. Hey, not bad. That's pretty close. And e to the 0.3, that's 1.350. pretty close. Okay? All right, ladies and gents. So I want you to try example 10 yourself. It's the same idea. Okay? And then the only difference in this case is our step size is a little bit wider, so 0.2. But I'd like you to try this, and then I'll ask you to try example 11. Try it, please, first before you come back and listen to me go over the answer. All right? We'll see you in class. So this is x minus y. So 0 minus 0.5 is negative 0.5. Delta y then takes the slope, which is negative 0.5. And you're going to multiply that by delta x. In this case, step size of 0.2. That's negative 0.1. So my new coordinate here, I'm going to add the delta x to that. That's 0.2 now. And I'm going to take the y, add to that the delta y, which is negative 1. So it's going 0.4. Keep doing this, 0.2 minus 0.4, 0.2. Just repeating the process. Do you feel like a machine? Do you feel like a computer? And then 0.4 minus 0.04, 0.36, I believe. Okay, now if I subtract, what's that? Ooh, 0.4 minus 0.36. Oh yes, I know, that's positive this time. Hey, it became positive. Interesting. So 0.04 times 0.2, that's 0.008. They're getting really small. So this is now 0.6, and I guess this would be 0.368. So that's my final answer of 0.6. If I were to draw these points now, 0, 0.5, so once again I'm drawing these points. 0.2 and 0.4, so I guess that goes here. 0.4 and 0.36, that's right about there. And 0.6 and 0.368, just a little bit higher now, like right there. So I guess my curve looks something like this. And then it comes back up just a little bit. Okay. And in part 11 it says sketch a particular solution of differential equation y prime x minus y passing through the points. So this one I said I gave you the slope field. All right, so now we're going back to what we did on page 1 and 2. And I'm asking you to now start here with this point and try to find the slope field. So if I were to continue going, it should look something like this perhaps. It seems to flatten out and go back up. Does that look pretty much like what we have up here? And the answer I think is yeah. But not exactly like, so it is approximate, but it looks pretty close.